octopus arms and the magnetic robots, but when we never thought of bringing them together. So that was a brilliant idea. So speaking of magnetic robots, I'm going to be kind of talking about that topic today, not so much about octopus arm. So in particular, I want to talk about our work on ferrofluidic robots, right? So magnetic fluids that you can control magnetically. So ferrofluids, is essentially, you can think of it as encapsulating iron oxide in a droplet being made of oil or water. You can custom make it any way you want with different properties. So and then the net magnetization without an applied field is basically zero. And then once you apply the magnetic field, you can magnetize and you can get them to move and do cool things, as you can see here. Our motivation for this was some of them are listed here. Lab on a chip applications are really the main focus of what we would like to achieve with this. But there's so much you could do beyond that. There's quite a bit of work done on this. Like starting maybe 15, 20 years ago, people have been kind of actively looking into this and doing a lot of really interesting work on controlling the shape, controlling the position, using different actuation techniques like electromagnets, permanent magnets, using different types of control, manual, PID, and so on, machine learning. What we would like to achieve here is to kind of go beyond this state of the art and kind of push it to 3D first of all. So everything was kind of limited to 2D. We want to go out of the plane. We want to do both position and shape control, and then we want to see what we can do with it, right? So some of the things we can achieve with this. In particular, I want to focus on two different topics. First, I'll talk about just the PID control that we use Bayesian optimization to optimize the gains, right? So we can automatically optimize all of the gains. And then I'll talk about our model predictive controller, which allows us to go beyond that. We can generalize the controller to different type of material, different size particles, and so on. And we can also test it in like flowing fluid, right? So it's not limited to static fluid as most of the people have been looking at. Okay, all right, let's start with the PID control with optimized gains. So this is just a snapshot of the system. I'll talk more about this in just a second. This is the overall scheme of things. Let me tell you what we're trying to control and then tell you how we control it. This is like on this slide, it's only showing you 2D, but you can extrapolate to 3D, and I'll show you both 2D and 3D results. So for position, we're trying to control the centroid of the center of this ellipsoid, okay? And then for shape, we're particularly interested in two shapes. We're modeling it as an ellipsoid. So we're looking at as the stretch length, how much you stretch this thing, and then stretch angle, like the angled orientation of the droplet, okay? Now, the way we control it, we essentially have a PID controller for each of these, right? So we have one for stretch length, stretch angle, and then position. We have visual feedback, right? And then that's how we close the loop. So that's pretty straightforward. And then in the Bayesian optimization case, which I don't go into the details in the interest of time, we basically automate tuning those gains. Tuning those gains could be very painful. We have a lot of those gains, right? So we would like to automate. So the way it works, basically, you collect some data, you learn the patterns, and then you optimize all of the gains automatically. So this is the setup. This is a custom-made 8-coil electromagnetic system. We got about 1 cubic inch space right in there. And so it's small, good for proof of concept experiments, but for like real world applications, we're going to have to expand it. And if you have time, we can talk about it at the end of the talk today. This is inspired by the design at ETH, Brad Nelson's lab. They were the pioneer of designing this particular coil system. And we have cameras all over the place, right? So looking from the top, from the side, anywhere we can look, we will fit a camera and we'll look. And this is what's happening in there, right? So remember I said there's 1 cubic inch space right in the middle of all of these coils. So that's where we put our workspace. We need to see through it, so that's why we have plexi on 2 sides. And then we cover these surfaces with silicone. Otherwise, the ferrofluid is going to stick to the plexi and it's going to make a mess. And it's going to mess up the visual feedback and all that. So, all right, let's move on. And everything is happening in a fluid, all right? So it's a droplet, and it's suspended in a fluid, right? The droplet could be made of water or oil, depending on whether it's made of water or oil. It's going to be moving in the other one, okay? So in the first, I'm going to be actually showing you results of both. Water-based ferrofluids and oil-based ferrofluids. Each one has its own pros and cons, so we can talk about it offline if you're interested. Okay, so let's talk about what we can do after we go through all that. So first of all, we can make multiple droplets out of a droplet, right? So if you need multiple of them, smaller, you can break them, and then whenever you want to bring them back, you can again bring them back and combine them and get a larger droplet. We can go through small channels, right? So if you have a channel that's smaller than the size of the droplet, we can kind of squeeze through it and they go from one side to the other side. This is happening automatically. We just go from one side to the other side, and it kind of detects the visual feedback is helping, of course, to switch the type of motion. It can collect items. If the items are wettable, it can go grab items and collect them and move them around. Okay, so and if they're non-wettable, we can still work with them. We can I don't want to spoil it, but essentially we can push them around, right? So we can sort them, we can push them around, and we can kind of move objects around as they need to be. Let's keep going. All right. We can also make pumps out of these things. Remember, we can stretch them, right? So we can control the shape. So we stretch them and we rotate them. All of a sudden, we have a pump. So this is a microfluidic channel, and this is food dye. So we're kind of pumping food dye from that chamber down to this chamber. If you can kind of see, it's getting greener and greener. And it's completely non-contact, right? So it's just a droplet there, and we're controlling it from far away. And the interesting thing about this is it's multifunctional, right? So it's not only a pump, it's not only a switch, it's not only a valve. It can pick, place, all of that together. Just a droplet can basically change functionality and do different things as needed. So this was all 2D, okay? Well, let's go to 3D. If this plays, there we go. So this is a demonstration of pick and place in 3D. So we had a whole lot of gains here. We used BO to optimize. We didn't do manual. The previous one, everything was done manually. So this one is using Bayesian optimization to kind of tune all the gains. So you can see, looking from different angles, that it's picking that object and it's dropping it down there, right? So and then it just leaves it there. Now, with this, we can do more. We can also do chemical testing, right? So if you have a microfluidic channel, you have different chemicals in there. You can take the droplet there, take samples of that chemical, and then measure the pH of it. And from there, you can kind of guesstimate what sort of material you're dealing with, right? So that's why this is one chamber, this is another chamber. And so we can kind of take samples from here and take it there to measure the pH. And then the same thing is happening there, okay? And this, on the right, you can kind of see that depending on what sort of chemical you pick up, you can kind of see how the pH is changing. Remember, I said there are at least two different types, two main types: water-based, oil-based. If we use water-based, it's going to be conductive, right? So all of a sudden, we can use the conductive properties of the droplet to now work with the electrical circuits, right? So all of a sudden, you have a switch, electrical switch, that you can move it anywhere you want, and you can connect different pins together, and you can turn different circuits on. So as you can see here, it's connecting two of these pins. So this circuit is going to be on for a second, then the other circuit is on, and then the third one is on, hopefully. There you go. So again, depending on what you need to do, there is so much that could be done. So this was all I wanted to tell you about the first kind of PID control with optimal gains and so on. There are shortcomings with that. The major shortcoming is if you change the material, if you change the size of the droplet, right? If you change anything basically in there, you would have to redo your gain tuning, which is going to take some time. No matter you're doing it manually or you're doing it with DO, even if you're doing it with Bayesian optimization, you have to run a few trials to learn and then kind of update your parameters, right? So that's not ideal. If you're sticking to the same droplet, same material, same size, everything, that's fine. Okay. But if you're planning on changing these things, or you want to have a system that's more generalizable and you can kind of work with different types of these properties, then this is the way to go. We were also able to test this in a flowing fluid, right? So remember, if down the road at some point you want to send these inside the body to do drug delivery, it's not going to be a static fluid, right? So you're going to have to be able to deal with it. And so that's something we tested. This is the setup for the flowing fluid. So this is the same workspace, and we just added a pump, and it's like you can see the water is being pumped through here, and then we can send overflow here, and that's how with just a single valve, a couple of valves actually, we can control the flow speed. This is the simple model that we have here. This is we're talking about MPC, model predictive controller. So this is magnetic force, and then we're considering the drag force, buoyancy, and gravitational forces. Did I click twice? No. Okay. And so these are some of the results, right? So first thing I'm showing here is no flow versus flow. And you can see it's following this pattern. You can kind of see the desired one and no flow and flowing. And the flowing one is doing nearly as good as the no flow case. All of the errors in all of the experiments I'm showing you is in submillimeter. So really tiny errors that we're dealing with. Okay, let's move on. So it does the whole tulip thing and then switches to the next one. So this is now trying different path in 3D, right? Going over a cube, tulip, spiral. This is all with flow, right? We're done with no flow. And then we're just showing the videos at different speeds, but you can kind of see it follows the trajectories pretty well. And you see the desired one versus the actual one, and we're plotting the results for different sizes. Remember, we said we can do this different size, different magnetization, different material, all of that. And I'll show more of those results in just a second. This is now results for different size. So 2 microliters, 3 microliters. We didn't really have to do anything extra. We just drop whatever size droplet we want there, and it just works. We don't have to tweak anything. Even if it's different material, all of that, it's going to be fine. And I'll show you different magnetization, different speeds, and it performs nearly well for all of those cases. Should have sped up these a bit more. Okay, so this one is different speeds. So if you want to just kind of control it at different speeds, and okay. This one is different magnetic field strength. Okay, that's fine. Let's move on. And this one is kind of controlling the shape and position independently, right? So you can kind of see the droplet is being stretched and at a fixed angle. Then all of a sudden we switch the angle, kind of follows the same tulip you're seeing from top and side. And then now we reduce the stretch, right? So we can kind of play with both stretch length and stretch angle and position. Like we're independently controlling all of those any way you want to see them. And this is all happening in flowing fluid, right? So I believe they tested velocities up to 1 to 2 centimeters per second, if I'm not mistaken. And that was just due to the limitation of the pump that we had in there. Okay. All right. So let me wrap up. We talked about ferrofluid control and like the 2 different types of control schemes and different things you could do with it for lab-on-a-chip applications, and down the road, hopefully, for drug delivery inside the body. The benefits of the second one I kind of highlighted with respect to the first in particular was it's more generalizable, right? So more robust. You have you have different size, different materials, and all of that, it will work out just fine. And this was, to the best of our knowledge, the first demonstration of this type of control in a fluid fluid for a ferrofluid droplet. With that, let me thank the team that helped with this. Reza worked on the first part of the project, the Bayesian optimization, the PID control, and Olga worked on the MPC part, and Mahdi kind of helped with developing the system. And these are our collaborators at different places all around the world. With that, thank you all for your attention, and I'll be happy to take questions.